Okay, in this video, we're going to look at some more solids of revolution, but this time our solids are going to be formed by what textbooks often call washers. If you remember in our last video, when we rotated a solid, we rotated a region around an axis, we were imagining the rectangles that were being rotated around, forming a cylinder, which we were using to help us come up with our formula. We're summing up cylinders when we find volume of this region. Well, we're going to have a similar idea here, except that these solids in this one are going to have holes or gaps in them. So they're not going to be completely solid. Let's say that we have, I'm just going to move our parabola a little higher. Let's say that we're cutting it off right here. So we have this region, but we still want to rotate around the x-axis. And so what's going to happen is that we end up with, if this is our reflected region, and I rotate, we're going to end up with a hole going through the middle of our solid. Hopefully you can kind of visualize that again, drawing these diagrams, not my greatest strength as a calculus teacher. We're still going to use the rectangles to help us determine our formula here. If I draw a rectangle, and I'm going to start at the axis of rotation. Here we're rotating around the x-axis. I'm going to start at the axis of rotation and go to the farthest edge of the region and draw in that rectangle. And if I imagine rotating that rectangle around the x-axis, of course that would be a solid cylinder. Then I'm going to start at the axis of rotation and draw a rectangle to the closest edge of the region. It's going to be a smaller radius. If I rotate that around, I get a cylinder. And that's the cylinder that we want to subtract out of the original solid. So again, if I took this whole region here and rotated it around, I would end up with something that was solid. But then what we want to do is subtract out this part inside to make that hole go through the solid. This first rectangle that I drew, we're going to call that the big radius from the axis to the outer edge of the region. And the second rectangle that I drew is going to be a little r. This is why I was using a capital R in the previous notes. Because we're going to use a capital R for the whole region as a solid. We're going to use a little r to represent the radius of the region that we're subtracting away. And so our volume formula is going to be pi. And you know what? I'm going to scratch this out. I really prefer to put the pi on the inside. I think when we stick it outside, we forget it. And I don't want to see that. If you want to put your pi on the outside, that's fine. But I'm going to scratch it out. Pi big R squared minus pi little r squared dx. That's how we're going to find the volume of these new three-dimensional figures. Again, treating it as if it's completely solid, subtracting out the whole. The big R is the radius to the farthest edge of the object, and little r is the radius to this doesn't really have enough room, to the closest edge of the object. So example number 1, find the volume if the region enclosed by y equals square root of x and y equals x squared is rotated about the x-axis. And they've given us the graph here. Here's my axis of rotation. Let me re-emphasize, whenever I draw these rectangles, I'm always going to start, let me color in the region just to help us a little bit. I'm going to start at the axis of rotation and go to the farthest edge of the region. That's big R. I'm going to start at the axis of rotation and go to the closest edge of the region, and that is little r. Now, to find out how long these things are, they're going to be, notice we're going, they're vertical We're going around a horizontal axis, so we're using top minus bottom to find out how long they are. My big R, the top of that radius is that square root of x, and the bottom, in this case, since we're just at the x-axis, is 0. You don't have to write that, but I'm going to go ahead and write it just to build that habit that we're doing top minus bottom. For the little r, its top is at the x squared, and its bottom is also at the axis of rotation, which is 0. So now I've got my big R and my little r. I can plug into our formula here. Integral pi times big R squared minus pi times little r squared dx. And I do need limits on my integrand. They do need to be x numbers because this is a dx. I can see that I'm starting this region at 0 and I'm stopping the region at 1. All right, in example number 2, we're using the same region, but we're changing the axis of rotation. This is being rotated around the line y equals 1. So we're rotating up this way. And I guess I should have tried to draw a picture. Let me draw you a little sketch of the region up here. Okay, so the region would come out looking something like that. When we rotate this way, it's actually going to look kind of similar because these functions are a little, well, they're inverses of each other. So we end up with a similar looking region rotating the other way. So if that kind of helps you visualize it, great. But remember, we don't have to visualize it. All we need to be able to do is draw in these rectangles. Again, I'm going to start at the axis of rotation, and I think that's really important to get these rectangles right. My axis of rotation is y equals 1. I'm going to start there and go to the farthest part of the region. That is big R. And then I'm going to start at the axis and go to the closest edge of the region, and that is little r. My big R, how long is it? Top minus bottom. If I look at this rectangle, the top of this rectangle is at y equals 1 minus, and the bottom of the rectangle I can see goes to the x squared part of the region. For little r, the top is at 1, and the bottom of that small radius, it's stopping at that square root function. There's my big R and my little r. So my volume is going to be equal to the integral of pi times big R squared minus pi times little r squared dx. And again, I need limits on the integral. They need to be x numbers. It's still 0 and 1 because it's the same region that we started with before. Now, one thing I want to point out at this point, if you set up your big R and little r's correctly, then one of the either the tops or the bottoms should be the same because it should always be the axis of rotation. In my first example, we were rotating around the x-axis and the bottoms were both 0. In the second example, we were rotating around 1, the tops were both 1. So either the tops are going to be the same or the bottoms are going to be the same, depending on if your axis of rotation is above or below your region. All right, let's look at example number 3. In this case, we're going to rotate around the y-axis. And so here's my region, and we're going horizontally this time. Axis of rotation is the y-axis. It's still going to be the same formula, pi big R squared minus pi little r squared, integral from a to b, but your limits are going to be y numbers this time. I'm going to draw in my rectangles, again, starting at the axis of rotation, which is the y-axis, and going to the farthest edge of the region. That's big R. And then I'm going to start at the y-axis and go to the closest edge of the region, and that is little r. So this integral does need to be in terms of y. Notice here, though, our equations are both in terms of x. They're solved for y. If I'm doing a dy integral, I've got to have my equations solved for x. So let's start with this one. So x squared equals y minus 1. X is going to be the square root of y minus 1. And we can go with the positive side of that because we are here in the first quadrant. And then y equals 2x plus 1. X equals y minus 1 over 2. All right. My big R. Now, in this case, instead of doing top minus bottom, we're going to do right minus left. On the right is the what's actually going to be that square root function minus the left, which would be 0, the y-axis. And then my little r, what's on the right is the linear y minus 1 over 2, and the left, 0. And now that we have big R and little r, we can write the integral. Pi big R squared minus pi little r squared dy. And I'm starting, notice since this is dy, we need to put y numbers on our integral. I'm starting at 0, and I'm going to go to 5.